Hi Year 12, here's our second lesson for the topic of vectors. In this video we're going to cover algebraic operations with vectors. So last lesson we looked at what are vectors and what are scalars, and we looked at the notation for vectors. We talked about the magnitude or length of a vector, and then we looked at the geometric operations, addition, subtraction and multiplication by a scalar, and then we finished off with vector equations. A vector can be represented on the Cartesian plane, and if it starts at the origin, it is called a position vector. It's like it's been positioned in place. And this is how we write it. OP, because O is the origin, is equal to 3 units horizontally and 5 units vertically. And this is called column vector form. You will also see this notation, but you will never see this, because 3, 5 with these normal brackets just refers to this point P, not the vector OP. Alternatively, we can write the vector in component form, which looks like this. This just means 3 units horizontally and 5 units vertically, because I and j are called base unit vectors. So I is 1 unit in the x direction and j is 1 unit in the y direction. Now, if a vector doesn't start at the origin, we call it a displacement vector, like it's been displaced. And in this case, all we do is find the rise and the run. So this vector, A, is equal to 6i plus 3j. Or we could write it like this. Now, if we want to form a displacement vector from 2 points, what we do is subtract the beginning from the end. So if we've got the vector AB, we're going to do B1 take away A1, B1 take away A1, and then B2 take away A2, B2 take away A2. Here's an example. Given the points A, negative 3, 1, and B, 3, 4, find the displacement vector AB. So all we're going to do is 3 take away negative 3, 4 take away 1. So the displacement vector AB is 6, 3. And look, it's just the rise and the run, isn't it? Now I mentioned this last lesson. Vectors are equal if they have the same magnitude and direction. And an easy way to tell this is by looking at their components. So let's write the vectors OA and CB in component form and show that they are equal. So OA is easy. It's going to be the coordinates of A, which is 2, 4. So OA is 2i plus 4j. And here we want rise and run. So 2 is the run and 4 is the rise. So CB is also equal to 2i plus 4j, therefore they are equal. Now last lesson we looked at geometric operations with vectors. We can also do algebraic operations with vectors. We can do addition, subtraction, multiplication by a scalar, and we can do a dot product. We can also do a cross product, but we're not going to cover that in this course. So here's addition. Given two vectors, A and B, A plus B will be the addition of the horizontal components and the addition of the vertical components. So here's an example. If A is the vector negative 1, 0 and B is the vector 4, 5, then A plus B will simply be negative 1 plus 4 and 0 plus 5, which is 3, 5. And geometrically, it looks like this. There's our two vectors. We're going to move this one over so it starts at the end of the first vector, and the combined displacement there, you can see, is 3, 5. Here's subtraction. Given two vectors A and B, A minus B, we subtract the horizontal components and we subtract the vertical components. Here's our example. A is equal to 1, 2, B is equal to 3, negative 1. Find A minus B. It is going to be 1 take away 3, 2 take away negative 1, which is negative 2, 3. Here it is geometrically. Do you remember how this goes? This one's A and this one's B. We want A minus B, so we're going to point towards that. Now we need to move it so it starts at the origin. Okay, so the components are negative 2, 3. And scalar multiplication. When we're multiplying by a scalar, we multiply all of the components. So If A is equal to A1, A2, then KA will be KA1, KA2. Here's an example. A is 2, negative 1. Find 2A. We're just going to double them. So we get 4, negative 2. And here it is geometrically. Here's A. And if we double it, we're going to end up with, look, 4, negative 2. Now the magnitude or the length of a vector is given by this formula here. And remember, this is its symbol, the absolute values around the vector. It's equal to the square root of a1 squared plus a2 squared. And this just comes from Pythagoras' theorem. Let's have a look here. It's the rise and the run. a1 squared plus a2 squared is equal to the length squared. And so the length is equal to the square root of a1 squared plus a2 squared. So let's find the magnitude of this vector. Now we know that vector A is 6i plus 3j, and so the magnitude will be the square root of 6 squared plus 3 squared, which is the square root of 45 or 3 root 5. Now, as well as calculating the magnitude of a vector, we need to know its direction. And we give this as an angle anti-clockwise from the positive x-axis. And the angle is measured in degrees between 0 and 360 degrees. So here's an example. Find the direction of vector A. So we want to find this angle in here. And we know that tan theta is going to equal opposite over adjacent. So theta will equal inverse tan of 3 on 6. And in the calculator, I get 26.6 degrees. Here's example 2. A vector A has magnitude 4 root 2 and is inclined at 135 degrees to the positive x-axis. Write the vector in component form. So this is what we know. The vector A can be written as r cos theta I plus r sin theta j. And this is the angle theta here. And r is the length of the vector. So if we just think about that for a second, this distance here, this length along the x-axis, would be the same as r cos theta, if this length here is r. And this distance here, up the y-axis, would be the same as r sin theta. Now all we need to do is substitute in 4 root 2 for r and 135 degrees for theta, like this. Now we are expected to use exact values here. So r is 4 root 2, cos 135, we're in the second quadrant here, it will be the same as negative cos 45, which is negative 1 on root 2. And sine 135, this will be the same as positive 1 on root 2. So substituting that in, tidying this up, we get negative 4i plus 4j. And look, negative 4i plus 4j. Now we can use vector methods to solve problems involving two-dimensional shapes. So here's an example. Determine the nature of a triangle formed by the points 2, 7, 10, 3, and negative 2, negative 1. So what types of triangles can we have? Equilateral, isosceles, scalene, right-angled. Let's start by forming the vectors AB, BC, and AC, just like this. So AB is going to be 10, take away 2, and 3, take away 7. And AC is negative 2, take 2, and negative 1, take 7. And BC is negative 2, take 10, and negative 1, take 3. All right, from there we're going to work out the magnitudes just by doing Pythagoras' theorem. So the magnitude of AB is square root of 80, AC is the square root of 80, and BC is the square root of 160. So we have an isosceles triangle here. We also have a right angle triangle, and you may not have spotted this, but square root of 160 all squared is equal to the square root of 80 all squared plus the square root of 80 all squared. So the triangle is isosceles and also right angled. So we're going to finish up again with vector equations. Remember when we did this last lesson? So AB plus BC, that was equal to AC. AB plus BC take away DC, we could turn that around. And when we added those together, we ended up with AD. So here's the question. Given AB is the vector 5, 1, CB is the vector negative 1, 0, and CD is the vector negative 3, 5, Find dA. So we're going to set up a vector equation using all of these letters. So dA is the same as DC plus CB plus BA. Let's have a look at what we've got. We have CB. We don't have DC, but we have CD. We don't have BA, but we have AB. So a little bit of adjustment. This is equal to negative CD plus CB take away AB. Let's substitute in. Now across the top we're going to get negative times a negative is a positive, so 3 take away 1 take away 5, and on the bottom negative 5 plus 0 take away 1. And so dA is the vector negative 3, negative 6. Okay, that's it for this lesson. Next lesson we'll look at parallelism.